This
Yeah.
conference will now be recorded.
Hello, everyone. So today we have Doug Arnold. Doug Arnold is a Principal Technologist at Meinberg USA. His duties include standards development, technical marketing, and pre-sales support. He's currently the chair of the IEEE Working Group, co-chair of the ISPCS PTP Plugfest Committee, and the co-author of the IETF Draft Enterprise Profile for PTP. Doug is an author of the 5 Minutes Fact About Packet Timing blog. He has over 20 years of experience designing and specifying precise time technology. Doug holds a Ph.D. In electrical engineering from the University of Illinois. Today, Doug is going to talk to us about what's new in the latest revision of the IEEE 1588. IEEE 1588-2019. Without further ado, Doug, let's start the presentation.
Okay, thank you. Okay, so first of all, we're talking about IEEE 1588-2019. So what is it? It's a document and a standard, and it defines the precision time protocol. A lot of people use 1588 and PTP interchangeably, but I think of PTP as the protocol and 1588 as the standard that defines it. The 2019 edition of the standard defined PTP version 2.1. And the name is associated with 2019. That's when it was approved by the Standards Board, but it wasn't published until 2020. Okay, so I want to talk about backward compatibility with previous versions of 1588 and a whole bunch of new features. I won't list them all right now, but a whole bunch of optional features that are new that were defined in this edition of the standard. Okay, first of all, backward compatibility. This was the #1 feedback we got when we started talking about a new version of 1588 is don't break it, and so we wrote it not just as a requirement for the project, but we wrote it into the bylaws of how 1588 Working Group operates. And there's the quote there that we shall ensure the resulting draft has the highest degree of backward compatibility possible with previous edition. So we took it seriously. And what we decided we had to figure out what we meant by that. And so what we meant was that if you take a device that is compliant to the 2019 edition of 1588 and put it in a network full of devices that are compliant to the 2008 edition, it won't break the network. Everything that was defined before basically works the same way. It's just that the new features, the older devices wouldn't have the new features, obviously, but the old ones work the same way, so everything still works together. That was the key. And we did not do that the time before. The 2002 and 2008 editions of 1588 are basically incompatible. Okay, so the first new optional feature, and it's important because it's in the common header of every PTP message, is a feature for profile isolation. So we had in the old common header in 2008, we had some reserve fields that we used into chunks to create something called SDO ID. And this is a standards development organization identity. It's a number that a standards organization can get. I have the rules here. It's 12 digits. It's given out by the IEEE Registration Authority. You have to go to them and convince them that you are in fact a standards development organization. A company can't get it. You have to really be someone who generates standards. And the idea is that your organization owns that SDO ID number, and so that any message, PTP message that has that SDO ID number is one of your profiles. And so if they're not implementing one of your profiles, then it's, then they do appropriate response as a device, like drop the message or whatever. So it performs complete isolation. We had these domain numbers before, but there was only 128 of them that you could use, and any profile could set up any range overlapping with other profiles. But if you have but the SDOI number would be unique to an organization. For example, the International Telecommunications Union or IETF or someone like that. Okay, so that is how we went about doing profile isolation. And I should point out, let me go back a second. Again, we use reserved fields in the message. That meant they were reserved for future editions of the standard, and so they should be ignored by previous edition devices, so it doesn't create a backward compatibility issue. We also did put in a minor version number for PTP. Before we only had major version, 1, 2, etc. Now we have 2.1, and the idea of making it 2.1 instead of 3 is to emphasize that it's backward compatible. Okay, so domains, that was the previous way of sorting out different PTP networks that might be occupying the same physical network. And they were, designed to be, every PTP domain is independent. It doesn't, if you're operating in PTP domain 15 and you get a message from PTP domain 37, you ignore it. But there are some interactions among domains that we realized were important. For example, if you want to implement multiple PTP domains for redundancy or multiple paths, if you want to transfer time from one domain to another in some device that is acting as a translator, you can do it outside of PTP and create a new PTP domain in a different profile or something. And it's also used for something called the common mean link delay servers, which we'll talk about in a little bit. So here's an example. I've got a robust clock, and what makes it, one of the things that makes it robust is that it runs a voting algorithm. So I've got 3 different PTP domains sending time, and I've got an implementation of a PTP slave in each one of these domains, and then we do a voting algorithm. If one of them is radically different than the other 2, which seem to be mostly in agreement, then we would say, okay, there's a problem with that time. We're not going to use that in our robust clock. So this is one example of what could be done with combining domains. And this is kind of similar with what can be done with NTP with its false ticker algorithm. Okay. Another thing that happened was we realized that people were making transparent clocks, switches that acted as transparent clocks that were modular. It was a blade architecture, or people were making SFP modules that can turn an ordinary switch into a transparent clock. And that created a complication, we realized, because in PTP version 2, we had 1-step timing and 2-step timing. 1-step timing, of course, is when a device can put an accurate timestamp in a message as it's leaving the port. It's all in hardware, and the delay is calibrated, and you just put the timestamp in as it's leaving, and it's accurate. Then the sync does not need a follow-up message if it's 1-step timing. If it's 2-step timing, you send the sync message, you note when it left, and you put that in the follow-up message. And there's a flag in the message to say whether it's 1-step or 2-step. So if you get a sync message, you know whether to expect a follow-up and wait for it. So in 2008 edition PTP, a transparent clock, for example, would be either 1-step or 2-step. And it would operate that way, or any other type of PTP clock would be 1-step or 2-step, except for the slave clocks are required to work with both. Now we realize that we could have a switch where every port is different. You know, these ports are 2-step, this port's 1-step, and you have to convert within the switch. And so we created a bunch of rules to make that happen. You know, so if it looks like this, for example, we've got a 1-step grandmaster. It's sending a sync message. It comes into a transparent clock. The ingress port is 2-step. So now it creates a follow-up message. So there wasn't one coming out of the grandmaster, but now there is. It sends them to the 1-step port on the output port. And what it does is say, well, I'm going to operate on the sync message. I'm going to ignore the follow-up and just send it through. Yeah. So initially the 2-step flag, that's the way it's indicated in the sync message, the 2-step flag is false. There's not going to be a follow-up. Then it gets set to true in the input port of the switch. And it remains true, even though this is a 1-step port, because the rules for 1-step are you usually just operate on the sync message and you ignore the follow-up and just send it through. However, there is also an option where you can collapse these. This 1-step port could gather the sync and follow-up message and compress them into one sync and then set the 2-step flag to be false again. That's also an option. So there's lots of combinations, and we realized we just had to make stepness a property of a port and not a clock. Okay, common mean link delay service. This is something that came from the IEEE 802.1 AS profile. Something they wanted, and they were developing in their profile at the same time we were developing this version of the standard. What in it was for the use cases related to manufacturing and industrial automation, they will typically have multiple profiles running, and they use peer delay, so they're just sending delay measurement messages between adjacent devices, to measure cable delays and things. And the cable delay is the same no matter which domain you're in. And so they only wanted to do that once and then pass it to all the other domains. So we had to create a multi-domain service. It was the first one we've ever had in PTP, and so we created this common mean link delay service. And this can be important if you have a boundary clock with a lot of ports and several domains. It can be a lot of processing overhead to do the peer delay messages, 4 times for each of 128 ports instead of just once. And so that was kind of the justification for that, and we created this feature. Okay, another thing that came out of the 1AS profiles, and this was kind of a theme. We had a lot of features that had been developed in PTP profiles by other organizations, and that seemed like good features. And we said, well, we're doing a revision. Let's put those in so they're available to other profiles, so people know about them. And this is another one. One of the problems if you have a long chain of boundary clocks, which is often the case in industrial automation, is you have a lot of settling time. And so you can have long transients that take a long time to work through all the different phase lock loops in a big chain of devices. Well, you can get around that by doing transparent clocks, which don't do any averaging, and so, but they also don't keep track of steps removed, and they don't build a timing hierarchy the way boundary clocks do, because they don't run the Westminster clock algorithm. So the 1AS folks came up with this type of boundary clock that had the benefits of both. It ran the Westminster clock algorithm and created a timing spanning tree, but it also did no averaging. It just passed all the information down to the end devices to do their own phase lock loop. And the way they did this is they just measured the difference in frequencies between all these unsteered oscillators and the different boundary clocks, And by accumulating that and passing that down to the end of the chain, you could figure out how to correct the time that came from the grandmaster. So here's kind of a pictorial picture of that. We have a grandmaster, we have several, a chain of boundary clocks, and we have a PTP ordinary clock in the slave state. And each one computes a neighbor rate ratio, the difference in frequency between two neighboring devices, using the peer delay messages. And then it sort of adds this up and sends it on down, and at the end device, it gets all of the accumulated differences in frequencies, and it can use that to adjust the time coming from the grandmaster. So from a timing point of view, it's equivalent to having transparent clocks, but from a protocol point of view, it's boundary clocks. So it's quite a clever arrangement. Okay, yet another thing that came from the 1AS group, special ports. So there are certain transport protocols that have their own built-in timing mechanism. And usually you can get better time transfer through these kinds of networks by using the built-in mechanism, because it's right there in the PHY of the devices, than if you just send PTP messages over that kind of network. And so, examples are, one example is Wi-Fi, and another example is EPON. EPON needed a timing mechanism because it uses time division multiplexing. Wi-Fi, they put it in because of devices that sleep most of the time and then wake up just in time to get a message or something, because they're on battery power. What we did is we created a media independent, media dependent interface for PTP. So the things that are related just for PTP and the things that are related to the transport media that it's going over are at that interface. And if we look here, using that interface, you could have a network where you start off with some kind of PTP network. You've got a PTP slave port in this special boundary clock, and then it's got a special port where say it's going over Wi-Fi to another boundary clock that has a Wi-Fi port, and it just uses the built-in Wi-Fi timing mechanism, but it transfers kind of the PTP metadata, timing metadata, and protocol information across through messages, so that PTP can be regenerated on this other side. And we don't, in this case, we don't send the sync messages or delay requests or anything like that. But we do send the announce messages, so you have that information, and then recreate those kind of messages on the other side. And that can be done for EPON as well. The details are in the 1AS standard for those two special ports. Okay, another thing that came from a profile, and this came from the draft enterprise profile in the IETF, and this is a mixed multicast unicast operation. So normally PTP is a multicast profile, and there is, however, a unicast variation that was created and used in telecom. But what some of the people from the finance industry said is we want the mixed multicast unicast. So we want the sync and announce messages to be multicast. So they just go out once from the grandmaster, they go through all the intervening devices and then go to the end clocks. But we don't want those clocks to have to get all the multicast messages intended for other devices. If you had 1,000 PTP slaves that were doing delay requests and delay response messages, that means 99.9% of the time when a PTP slave gets a delay response message, it's for some other clock. It looks at it and says, oh, that's not for me, and throws it away. So it does that over and over again until it finally gets its own. And in finance, they didn't want the application to be spending all this time looking at messages that were for someone else. So they wanted this kind of behavior. This was something actually was considered for earlier versions of PTP, but not for various technical reasons, not implemented. But it is now one of the modes of working. Okay, another thing, as PTP is getting implemented in the field and getting used more, people start realizing, well, we want to monitor the network and make sure it's operating correctly because we're using this for critical infrastructure. We need to know that the timing there's no problem with the timing. So various forms of monitoring were being worked on, and two things that were added to the standard. One is performance metrics. So we created a feature where there was these standard metrics for a PTP port that could be reported in a standard format. And the idea is that if multiple equipment vendors implemented this, then one management tool could easily gather all these statistics and counters, and they'd all be formatted the same. It'd make it easy to create a uniform view of the PTP network. So and this was driven by the way things are done traditionally in telecom networks. They have a 24-hour average for each metric, plus 24 hours worth of 15-minute averages. Altogether, there was 37 different metrics defined, and you're allowed to implement any of them. You don't have to do the whole thing. If you do it, you can just pick the ones you like. But for every quantifiable variable, there's average, minimum, maximum, and standard deviation. And if it's something that's an event, you have a counter for the events. And here's some examples. Our average offset from master, minimum mean path delay. That would be when you're using the delay request response mechanism. Maximum mean link delay if you're using the peer delay mechanism would be one that would be relevant. SyncRx, this is a counter. How many sync messages have you received? And like I said, there's 37 of these, and it can be, if you do the whole thing, it's quite a bit. 37 different metrics, plus a 24-hour average, and probably want to keep the last 24-hour one as well till the new one's full, plus all these 15-minute averages. So it's a lot. But for some applications, they'll want all of it, and others they'll just want certain ones. Another thing that was created was called slave event monitoring. And yes?
Yeah, one question on these performance monitoring, those PM counters. What is not clear when I looked at this was, this is good, the equipment can, and the ports can calculate all of these counters, is from accessing those counters. It wasn't clear if 1588 had in the PTP management client come up with some kind of a TLVs that allow, a management system outside PTP to query these counters. Any thoughts on this?
Yes, we did not create PTP messages just to carry this information. It was thought that it would be put in a log and then archived in some standard logging protocol rather than something we would create.
Okay, so from the management, I think section 16 and 1588, nothing to your awareness was done in there, right? To
That's right.
Okay, thank you. Yeah.
But you could create a Yang or MIB data model and put the information there and export it that way, or just syslog or something.
Thank you.
Okay, good question. Because slave event monitoring, this has to do with kind of verifying that a PTP port in the slave state has the right timing. And so there were some TLVs that could be put in signaling messages or whatever. In this one, the TLVs were defined, but it's sort of like a half-done monitoring mechanism. It's not really complete. But that's as far as we got when it was time to get the revision finalized. So I should go back and say, but they're basically you can gather timestamps received by the slave and computed data like its offset and delay, and then compare those to each other and verify that everything makes sense. The slave is operating correctly and seems to have good time. So that's the idea with these TLVs. Okay, a big part of what we did was high accuracy, and it was all based on the work at CERN. This is a picture from one of our 1588 meetings. Several members of the 1588 working group underground at the Large Hadron Collider in CERN, where they developed the White Rabbit extensions to PTP. And Maciej Lipinski was the lead scientist with that, and he spent a lot of time putting the various things that made up White Rabbit as optional features in PTP. And of course, they're able to achieve sub-nanosecond phase alignment among nodes in their networks using these techniques. So there's basically three things that you have to do to turn PTP into White Rabbit. So they don't run a best master clock algorithm. Everything is manually configured. This port's in the slave state, this port's in the master state, etc. So that was a feature, and we put each of these in as a standalone feature, so you can take some of it rather than the whole thing, and you get some benefits relating to accuracy, but maybe you don't need sub-nanosecond, you just need 10 nanoseconds or something. Another one is layer one synchronization. An example of layer one synchronization is synchronous Ethernet, where you basically lock all the clocks of the Ethernet of your Ethernet network together. And the last one is asymmetry calibration. So you calibrate the asymmetry of the various ports, asymmetry and of the various cables, because cables have some asymmetry. If it's a copper cable, there's a different number of twists in the different twisted pairs of wire. If it's a fiber, and you're using different colors, there's a slightly different. So you might use a different color for one direction compared to the other direction, and that would create an asymmetry. Because of course PTP, like NTP, assumes that the forward and reverse one-way delays are the same. It has to make that assumption, or it doesn't have enough information. But there can be asymmetries, and you calibrate them out of the cables and of the PHYs, because Ethernet PHYs have asymmetries built into them. And once you've gone through the trouble of calibrating them, you need to make sure that those calibrations remain valid, and that's why all the PHY clocks, transmit and receive clocks, are all locked together in a physical layer, frequency locked network. So that way they don't drift apart over time, and then you have to recalibrate. They maintain that calibration. So the calibration is not so valuable unless you also do the physical layer synchronization. And there's like 100 pages of detail on this, so I don't have time to get into it all right now, but it is in the standard. And more things are being worked on now for future revisions or amendments. Okay, then there was security, was something we wanted to address. In 2008, we had this experimental security mechanism. Is there a question?
Yeah, for the accuracy TLV, I think there is some work being done in 1588A, right?
Yes, that's not related to this calibration and the high accuracy. That's related to measuring things like how much, right now in the best master clock algorithm, all we use to decide what is the best path from a grandmaster is which one has the fewest boundary clocks, the number of hops. But you could say, well, not all boundary clocks are the same, and we would like to add up the amount of error each boundary clock gets, and then we put it in this enhanced accuracy metrics TLV that goes through all the boundary clocks. And so when they make decisions, they could use that more detailed information instead of just the hop count. And you can add transparent clocks, which right now don't contribute to the hop count, but there's a field in that TLV for things like number of transparent clock hops. And there's a whole bunch of fields for different kinds of noise, static noise, dynamic, transient, and all of these could be used in an alternate TLV, alternate BMCA, which profiles can define a different BMCA than the one that's the standard one in 1588. And that we are in the process right now working on an amendment to give some more guidelines on how to use that to create an alternate BMCA for a profile. But that's not in the 2019 edition that I'm talking about now. The TLV is in, but the guidelines on how to use it are not. And it's expected that it would be used. There's two things you could use it for. One would be in an alternate BMCA, and the other is just as a monitoring thing. I look at the accumulated error that has shown up through all the various switches by the time it gets to the end clock, and I can just say that exceeds my error bound. I can raise a, send a notification in the management interface, or I could look at it and just log it and say, okay, this is what I was getting. And I don't think I actually talked about that, so I'm glad you asked the question. But TLV was defined in 2019 edition of 1588, but we're working on the guidelines on how to use it. So thanks for that question. Okay, security. In 2008, we had an experimental security mechanism, Annex K, that no one really implemented, and it was labeled experimental, and some security experts looked at it and said there's some flaws. So basically we scrapped it when 2019 came around. We started over, and we had two things. One is we had a TLV we defined called the authentication TLV, which I'll get to in a minute, and we had a bunch of informative information, what we called the 4 prongs of security. The chair of the security working group put 4 prongs in until she could replace that with something that sounded better, and nothing ever came up, so it's still in there. 4 prongs. The first one is things to keep in mind when you're doing PTP over IPsec or MACsec, and this has two. It could be a security mechanism where you set up IPsec and MACsec associations and do PTP over these. A security mechanism could be built that way. But you could also have the situation where it's a mapping, where PTP has to go over IPsec and MACsec because that network is running everything over one of these. And so it just has to be made to work. So there's some recommendations related to that. And then there's recommendations for using this authentication TLV. The authentication TLV is something you can attach to PTP messages, but it doesn't say anything about how you get the keys to the different clocks. And so there's some information about a couple of key exchange mechanism. It's a little underdeveloped, so that's something we're working on as well. But there's some information about two in particular, group domain of interaction, GDOI. This is something already used in power substations for other SCADA system message types. And so it would be sort of a natural to use it. And what the idea is, it's a group, there's a group key, and everyone who's authorized can get the latest group key and then use that. And that is one way to deal with things like boundary clocks and transparent clocks, where every switch along the way has to be part of the secret. And then there was something called Tesla, which is also, and these both come out of the IETF. And the idea of Tesla, it has very strong encryption if you can wait a little bit. So it sends you a message, it can't be altered along the way, but then it says, okay, this key is now no longer being used, here it is. So now you can verify the messages you got recently. So the trick is that the keys are not distributed until they're no longer being used. So not a lot of details presented. That's something we're working on. And then there was a lot of recommendations relating to redundancy, multi-master, multi-path PTP. These are helpful, necessary but not sufficient to defeat delay attacks. And delay attacks are sort of something unique to timing, because if a switch just holds up messages in one direction but not the other, they can create an asymmetry that can't be detected by the timing protocol, and it can't be detected by cryptography because they don't have to alter any messages. They just have to hold on to them for a little while. So delay attacks is sort of a unique attack on timing systems. And you want to combine some kind of cryptography with redundancy in order to defeat that. And then there were some recommendations on the use of monitoring. Monitoring is good for security, but just for general robustness, Yeah, I mean, since I'm on that topic for a second, monitoring is something I strongly recommend. Here's what happens in a PTP application. They're adding PTP to some kind of network. They get all their best, network architects together and engineers, and they do their homework. They test it out in the lab, they put it in, they check it out, everything's working, and then they go away, they're working on something else. Well, the timing is using the same network as all the other applications, which means things are changing. And so over time, something that worked could stop working. More switches have been added, and now that the error accumulation is too high, or different kinds of traffic is causing more queuing noise. And so things can happen. So you really want to monitor something you put in, and then you can make sure it's still working the way you wanted it to.
You mentioned to me before that you are working on, or the group is working on 2 security profiles.
We're working on new. I wouldn't say profiles yet. I would say key management, automated key management systems. So there's going to be an amendment with a lot more detail on how to use GDOI with PTP. We're also helping the IETF out. We have a couple of proposals in the IETF for using a TLS-based key, a TLS-based key management system. So for example, up here in prong 1, you can use an IPsec on layer 3 PTP, but you have to go and set up IPsec associations between all the devices that are going to talk to each other, and then tear them down and then refresh the keys and all that. And so usually you want something on top of IPsec that manages all that, that is protocol specific. And GDOI is an example of that. It's based on IPsec, so it uses IPsec technology to establish a secure connection, PKI techniques and digital certificates and all that. So you can establish a secure connection with a key server and get a key, and the node that's getting the key can be authenticated that yes, they are someone who should be getting this key. But you want something that's PTP aware that sits on top of IPsec, or it could be TLS. TLS is used in a lot of protocols on the internet, like web, HTTPS. The S in HTTPS is TLS, transport layer security. And so there's a couple of proposals in the IETF to create a TLS-based key management system for PTP, which we would also have a PTP amendment to talk about. But those are things that are being worked on now. If you want something that's ready, the only thing that's really ready is GDOI. Or you can do your own. You can use IPsec or TLS and as a foundation, and then build your own key management on top of that. Okay, so I talked about redundancy and monitoring. Yeah, so again, this was a step in the right direction for security, but it wasn't complete. It was something we had to stop when it was time to publish the new edition, and this is how far we got. Okay, here's we originally called this a security TLV. It's now in the edition, it's called the authentication TLV, because it really is used to authenticate a message and prove that it hasn't been changed en route. So it has a security parameter index. Let's say you have negotiated some security algorithm and you have some parameters associated with that, and that is a table in your device saying, okay, this algorithm and these parameter values are indicated by this security parameter index value. And then a key identifier, this is a number that it's not the key, it just refers to which key we're talking about. So if you were able to get the key, you got the key ID with it. We didn't, the security, this one's a security parameter indicator. The SPI security parameter index, that just says which of these optional fields are going to be included. It's just a flag field. So one is the disclose key. This is to support Tesla. After you are no longer using the key and you want to disclose it, you can put it in here. There's an optional sequence number, which mostly we probably won't use because all the PTP messages have their own sequence numbers. You want to use sequence numbers to prevent replay attacks. And then there's a reserve field we just put there for future revision of the standard for whatever we forgot, which we won't know until it gets out there. And then the hash code, the ICV or hash code that is based on everything in the PTP message up to this field. And then you put this in, and so people can recompute the hash for the message using the secret key that you have and verify that it wasn't changed. Okay, so in summary, there's a whole lot of fields we have, a whole lot of options. just to reiterate, we made sure that PTP v2 and PTP v2.1 devices can work together. That was a critical requirement for this effort. We added features for robustness, profile isolation, inter-domain interactions, authentication, TLV, the standard metrics and slave port monitoring. These are all things that can help make a more robust system. Features for accuracy, the manual port configuration, calibration, and layer 1 synchronization. And you could argue layer 1 synchronization helps with robustness as well, because if you're running something like synchronous Ethernet, and then you go into holdover, GPS is jammed, you're not getting time, but the Grandmaster has a very good oscillator, and you can be connected to that oscillator through layer 1 synchronization, and then each and every node can have good holdover. Or you can even make the primary reference clock for synchronous Ethernet to be different than the Grandmaster. So if the Grandmaster's fault, going away because it's in fault, or a switch it was connected to is faulty, then you could still have the primary reference clock frequency and have better holdover everywhere in the network. So that can be also a robustness feature. Features for flexibility, modular transparent clocks, and then these cumulative frequency transfer that allows you to do clever versions of PTP where you have the best of both worlds. When people always ask me what's better, boundary clocks or transparent clocks, and well, in some ways these 1AS boundary clocks is the answer because they have the best of both worlds. Special ports, if you are connecting to a network that has a built-in timing mechanism like EPON or Wi-Fi, the mixed multicast unicast operation that cuts down on sort of traffic in the multicast network. You have a lot of PTP slaves and you're doing delay request response. Manual port configuration, that was also listed under accuracy, but you can use it just for convenience. I don't want to run the BMCA, I'm going to just manually configure everything. And inter-domain interactions allow you to create things like protocol translating devices and whatnot. So that's what I got for you today. Thank you for your attention. If you didn't get a chance, I'm happy to take some questions, but if we don't get to them, you can always send an email. I find it helpful when I get questions about PTP because it lets me know what needs to be clarified in the standard. So any questions I can answer right now?
This is Arthur. Thank you very much for your wonderful presentation. I am not probably the best knowledgeable person, but I believe the ORAN standard, one of the standard that we follow, they use the older version of the 1544. Can you comment on how well the 2019 version is actually being adopted by other vendors that leveraging the 1544, like for example, some of the Facebook Engage product line, like a DCAG or Open RAN, you can call it Open RAN, or ORAN. I don't think they are adopting 2019 yet.
That could be, most of the information I get from this is related to profiles that people are working on, and a whole lot of profiles were created for the 2008 edition. And what I'm finding is that gradually, usually the first thing that happens, for example, in the ITU, which I'm also a member of, the first thing they did is, can we just make a minor change in our profile so that it works with either 2008 or 2019 edition? And then they start looking at the new optional features and say, what do we want to add to our profile? So I think it's just sort of happening now. I've been in contact also with people at the IEC in the power industry. They're looking at making an IEC, version of 1588. Basically, they just do a new cover page over 1588 and call it an IEC 61580 or something. That's something they've done before, and they're looking at doing that. So once they have that in place, then the power industry could start looking at new profiles. I know SEMTI is looking at, they're currently in the process of revising their 1588 profile, and they're going to base it on 2019. SEMTI is the broadcast Society of Motion Picture and Television Engineers, I think is what it originally meant, although now it's sort of broadcast and streaming companies use it. And they're interested in some of the new features like security, so they're definitely going to want to use 2019. Others are just happy with what they have and it's working for them, and they're staying with 2008 for now. And because they're backward compatible, that shouldn't be a problem. They should be able to go on that way for a while until they want one of the new features.
A lot of the options,
I think eventually.
I just say thank you for the clarification, and then sorry, Michelle, interrupt your comment. Yeah, I basically I want to say is that we are still in following, you may call it old version, because the old and new are all relative, right? Obviously 2019 is not latest, but I also highly encourage you, we do not jump to anything new just to call it better. We need to prove that anything newer is better before it become adopted for the implementation of the product. Yeah. That's what I try to say. Yeah.
One thing.
Yeah, that's a good point. The first 3 editions of 1588, including 2019, the latest one, the working group was chaired by John Eisen, formerly of HP Labs, who created this protocol. And that's what you said were exactly his parting words. It's like, I'm done with this, I'm retired. Just, if you're going to add anything, don't just find another way to do the same thing. It has to be better in some use case in a way that's critical. So that's one of our guiding principles. The other thing is, 1588, because of all the different industries that use it, you could argue it's not even a standard, it's a standard menu, superset. And that's why we have to have profiles in order to create things that we can ensure are interoperable. And so profiles can pick and choose from these features and say, every profile says, yes, we want these options. No, we don't want these. And these third category is like, they're allowed but not required. But usually you want to have the fewest, a good profile, you want to have everything like required or forbidden and not a lot of options, just to make sure things stay interoperable.
Michelle, do you want to ask a question?
Yeah, I know we're out of time, but I just wanted to point out, for instance, like a lot of the things and thank you, Doug, a lot of the things you mentioned are these features are optional, but one thing in the normative section that I came across is the generation of the clock ID that changed between 2008 and 2019. So in 2008, you would put FFFE in between the 3rd and 4 byte. Now the rules are different. And what we have seen now is when you put for instance, a GM that is 2019 compliant, and you've got an ordinary clock that is 2008, some of these clocks filter on that FFFE to make sure that the clock ID is properly constructed. In that case, then it just doesn't work.
Yeah, so that was a place where we had to break backward compatibility, and that was because the IEEE registration authority came to us and said, you can't do this anymore because we've figured out that it's possible to have duplicate clock IDs. And so you have to change. And so it's like, okay, well, there's no choice then. We have to make that change.
Yeah, so
and yeah, some
I think this is a
implementations might
point.
have to make an adjustment. Yeah.
Yes, thank you, Dar. You know, I think this point is important. You know, and then maybe it may sound like a joking. You know, I also probably is thinking about the same thing. Say I might just retire with the 2008 version. That's good enough for me. 2019 is Michelle's problem now. But yeah, I don't think 2019 is ready for prime time quite yet for other product, particularly the telco product line that leverage the 1544. Yeah. But obviously, we do see new use cases, new value, new advantages. But we just need to be very careful for the telco product line. I don't think 2019 is there yet. That I think my question is more about what do you think or when do you guess the 2019 version of the standard will become more adaptable by the product that is go to the market, you know, maybe 5 years, 6 years, something like that.
Well,
okay,
it's being
so, yeah, go ahead.
the telco profiles are already being revised so that you can use either, and I think that's one of the places where it will play, because now we're talking about 5 nanosecond boundary clocks to support 5G, and you're going to need some of these high accuracy techniques.
Yeah. By the way, I think we run out of time. Yeah, must be Amin is trying to say we need to wrap up the meeting.
I wanted. We started a little bit late, like we have another 4 or 5 minutes. So I was like going to ask like 2 more technical questions. Like one was, do we have any mechanism to basically synchronize the transparent clock yet in these standards, or nothing is provisioned for it? And the second one is like this is something that my team and I we're working on. It is the calculation of the uncertainty, basically on the end node. Do we have anything also in the TLV that can help with that, or like we can basically come up with things and basically propose them in IEEE and then push them forward?
So on the first question, yeah, when they did White Rabbit, they did layer 1 synchronization, but it was a proprietary mechanism because at that time synchronous Ethernet was not accurate enough, wasn't stable enough. Since then, synchronous Ethernet has been revised so that there are more higher stability levels of service, and so it could be, that's probably the best way to do it, to use synchronous Ethernet. The other thing having to do with calculating the error, so if you use the authentication or the enhanced accuracy metrics TLV, it would have to be specified in a profile that it was supported by all the boundary clocks and transparent clocks, because right now most of them don't support it. But if you specify that in a profile, that they will all add their own inaccuracy. So then you could get at the end node, it could look at the accumulated inaccuracy and say, okay, it looks like the worst case timing is still within my spec, and I can report that to a monitoring function. But there are other ways of doing monitoring. You can put, you know, some people have larger networks, they have some additional devices that have some other kind of way of getting precise time, that they measure the time at that point in the network. Yeah. And yeah, using GPS or something, and then they say, yep, it's good here. I think this is the worst case position of my network, so it should be good everywhere. And there's other ways. Reverse PTP is something people do, where they transfer time back to a monitoring node from a PTP slave.
Yeah, like in our architecture, basically we're thinking about probes. You have some probes that they have GPS, and they do hardware timestamping. They do external hardware timestamping, while PTP is on the go. And then there is a measurement that It's based on statistics. It's an estimation of the standard deviation, and then you look at, is it still like, is this model still accurate or not? Is it still like giving us the confidence that we're looking for? And this is an ongoing process, basically.
Yeah, you have to be careful if you have queuing noise. So if you have switches that don't have on-path support, standard deviation might not be a good statistic because that has very skewed noise properties.
Yeah. Yeah. No, we're fitting it like in we're basically fitting it in a Gaussian thing with a very conservative way. Like basically everything goes through like kernel estimation, and then you put it with a Gaussian curve that can cover the whole thing, and then you go for standard deviations, basically. So,
Okay.
but the only unknown I have here to basically make this more predictable is my transparent clocks, that they can be like, and the thing is like I don't have sync E, so I have to run some other way. And like right now, that probe is my only way to see if like basically a needle in a haystack. Is there, and you're looking for it with a magnet, basically. Is there something here or not? Something wrong here or not? Is like basically.
Yeah, and with transparent clocks and boundary clocks, I've heard more reports of issues because these are part of switches and routers, and they have many protocols to implement. And somewhere on page 3 of the requirements is PTP is listed and goes to a junior engineer or something who's never done a phase lock loop. This doesn't always happen, but sometimes it does. And there's been times where I've had to tell customers to turn off the boundary clock function on your switch because the timing will be better without it.
Yeah.
So I strongly recommend it. Transparent clocks and boundary clocks get tested in the lab.
We don't even have boundary clocks. Yeah, we don't have boundary clocks. In our architecture, we have like hundreds of thousands of machines with no boundary clock, all transparent clocks.
Okay, well, even transparent clocks, I would just test them in the lab, make sure that their contribution to the error. Transparent clocks are a better bet because then there's no phase lock loop or anything like that. It's just phi asymmetry and and timestamp resolution noise, which is one is it tends to be uncorrelated, so it does tend to fit into a Gaussian, and then the other is it's bounded, it's not that big.
Yeah. Okay, so any more question before we wrap it up? Okay, hearing none. Okay, Doc, thank you again for the presentation, and the recording will be basically on the ocptap.com available. Thank you, everyone.
Great.
Bye,
Thank
everyone.
you.
Bye-bye.
Thank you.